Hello, I'm Wanxian Lim from Chungang University. I'll present our work, CPS-Prompt, Critical Patch-Aware Sparse Prompting with Decoupled Training for Continual Learning on the Edge. Continual learning is now expected to run on-device, robots, drones, phones, where cloud retraining is privacy-restricted or infeasible, but edge devices have tight memory budgets, and excessive activations can crash training. The plot on the right shows the trade-off on a Jetson Orin Nano. Existing methods are either accurate but heavy, like C-Prompt, or fast but less accurate. We aim for the upper left. There are two research gaps. First, prompt-based continual learning methods like C-Prompt and OS-Prompt focus on accuracy, leaving training time memory unaddressed. Second, generic token reduction, TOME, patch dropout, cuts activations but is task agnostic. It discards patches that matter for the current task. We need task-aware sparsification that preserves PCL accuracy while cutting memory. Our research question: can prompt-based continual learning be made memory efficient enough for on-device training without sacrificing accuracy? We make 4 contributions. CPS-Prompt, the first PCL framework explicitly targeting training memory. A task-aware CPS module, a decoupled DPCT training module, and validation on real Jetson hardware across 3 benchmarks. Here's the framework. On the left, critical patch sampling. The frozen query encoder produces a critical score per patch, and we sample a small subset before the prompt forward pass. On the right, decoupled prompt classifier training. Phase 1 trains the prompt and classifier on sparse patches. Phase 2 fine-tunes only the classifier on full patches. 2 ideas, complementary. Let me unpack CPS. For each patch J, the critical score is class attention times value norm, computed from the final query block. This captures both relevance and feature strength. We apply softmax with temperature tau, then sample K patches per mini-batch from a multinomial distribution. Why this works on edge: K is much smaller than N, so attention cost and stored activations drop. The selection is task-aware, and it's training-free. All signals come from the frozen backbone. DPCT splits training into 2 phases. Phase 1. Input is sparse patches from CPS. We train both prompt and classifier. The model learns task-adaptive features under reduced input. Phase 2. Input switches to full patches. We freeze the prompt and only fine-tune the classifier. This aligns the classifier with the inference distribution. And since there's no gradient through the prompt, backprop is much faster. This is the main accuracy table. CPS-Prompt sits within roughly half a point of CODA-Prompt across all 3 datasets: CFAR 100, ImageNet R, and Cub 200. C-Prompt is a bit higher, but as we'll see next, at a steep efficiency cost. Efficiency on the Jetson Orin Nano. C-Prompt, the tallest bars, uses massively more memory, training time, and energy. Ours, the hatched bar on the right, is consistently the lightest across all 3 datasets. The takeaways: 1.6 times less peak memory, 1.5 times shorter training, 1.6 times less energy, for a 2% accuracy gap. How does each method degrade as memory reduction pushes harder? Top row, accuracy. TOME collapses past 40%. Ours, the red star line, stays close to baseline even at 60%. Bottom row, training time. Ours is the lowest across every reduction level. Robust on both axes. Ablation at half sparsity on ImageNet R. CPS alone beats patch dropout by 1.8 points at the same memory. Task-aware sampling matters. DPCT cuts training time by roughly 19% by freezing the prompt. Combined, the highlighted row, they recover nearly all the baseline accuracy with all the efficiency gains. To conclude, training time efficiency matters for edge continual learning, not just accuracy. Task-aware sparsity beats task-agnostic token reduction. Decoupling fixes the train inference mismatch. And we validated on real edge hardware. Paper and code are at the links shown. Thank you.